All right, so the last video cut out a bit too early, and I'm going to go over some of the concepts we were talking about. A lot of it is covered in that video. I just start with a quick overview of what we discussed. Basically, these are definitions and introductory material, and then to maintain the flow into our actual discussion about different statistical learning algorithms. So we said that the goal, the focus at the beginning is supervised learning. The goal is to find the relationship between some set of data that you have from the input and the outputs that correspond to that data set. So if we say y is the output and x is your input data, we want to see what that f could be, right? The function that describes the relationship between the input and output. That function may be complicated, it may be linear, nonlinear, it may be it may not have a closed form expression, but there are degrees of freedom there that we want to go and play with and turn these knobs so that we try to figure out what is the relationship between input and output. So we said there are two types of problems in supervised learning, regression and classification. Regression is where you are trying to estimate a continuous variable, like the example we used was the house prices in a region or the temperature in a certain place. Classification is where you have a limited number of classes and you want to label your data to belong to one of those two classes, right, or multiple classes. So it's a yes/no question, 0, 1, color, categories. You're talking about categories instead of values here. And then we have unsupervised learning that we will cover later on. Now, we said there are a bunch of different algorithms we can choose from in supervised learning. Unsupervised, it's a bit more limited. And we're going to focus on the ones that practically are easy to implement and easy to understand and easy to troubleshoot. So if you go and look at the literature and then let's say the news, technical news about these statistical learning or machine learning activities in the field, you hear a lot about neural networks and support vector machines and those kinds of advanced algorithms. But the challenge with those is that they are hard to troubleshoot. If something goes wrong, it's not really easy for us to go and figure out what the problem is. What I'm going to do instead is that I'm going to focus on those that, in terms of accuracy and precision, are very close to the most sophisticated algorithms out there, but they're easy to understand. So even as an engineer, you have an intuitive intuition about how these algorithms work. And those are logistic regression, KNN, naive Bayes, and decision trees. We'll talk about the problems that we may have here. And then we went and talked about definitions, how the terminology that we're going to be using in this section of the course. So number of samples, it's M, so it's the data set that you have, right? So, and you want to use this data set to come up with a best description between input and output. We have M samples. Each sample has a set of data, inputs, and one output that corresponds to that input, right? So that output could be Y, could be categorical, or it could be something that is continuous. It could be, let's say, the house price or the color of something. And the vector xi that contains all the input to your algorithm, it's usually features. It's not raw data. It is features that you have calculated from the raw data. You have n features that you extract from that data or a portion of the data, that raw data that you have. And usually we add a first element at the very top of this vector x naught, whose value is just 1. And then this makes the input vector n by 1, n plus 1 by 1 vector, right? So the first element in your feature vector x naught is set to 1 in most cases, in most machine learning applications. That's going to help you to account for offsets and biases and things like that. In some cases you don't need it, but in vast majority of the cases you have a 1 at the beginning of your feature vector, and then x1 to xn are the values that you calculate from data. You can put all of your input vectors, just transpose them and put them on top of each other, create a matrix that contains all of your input data set. In that case, therefore, that matrix will be of order m times n plus 1. And then you have a vector y that tells you, for that set of input features, this is the output value. So this vector will have a dimension of m by 1. And this is basically what you feed into your algorithm. So what the goal is to come up with a function that takes that data matrix X or vector X and produces vector Y or matrix, well, basically single value Y or vector Y. So how do we do that? We create a weight vector. These are numbers that we want to figure out what they are. We don't know them at the beginning. Our function takes these weights and does some mathematical operation on the feature vector that we had to produce the output. So this is going to be how the this assumed function would work. You have a feature vector x, you have a weight vector, and you have a single output. At this point, you know x and y. You do not know w. And then what you do is that these w's you go and adjust. So this is a vector n plus 1 by 1. You go and try to adjust these w's such that your function f feeds to your data, produces those y's with the least amount of error possible. And that's the learning process, right? To figure out how you're doing it, if your algorithm is basically moving in the right direction or not, you need to come up with a way of penalizing wrong estimations or predictions, right? So then you define a cost function. You say, my function assumed the output would be this much based on this input vector, but the true output is this much. And how do I penalize that? Let's say if there is a difference, how do I penalize it, right? So that cost function becomes very important, because minimizing that cost function is basically your training. So choosing the algorithm will tell you what kind of an f you're dealing with, what kind of a function you're dealing with, and the cost function will let you modify the weights so that your function fits your data best. So these two go hand in hand. The choice of the function and the choice of the cost function go hand in hand. Our goal is to minimize the cost function. So that J that you see over there, our goal is to minimize the cost function based on the data we have and hopefully on the data that we will see later. And we said, well, in reality, what matters is that how your function behaves on new data, on data that it will see in future. And for that reason, you basically want to train your algorithm with a little bit of data that you know the input and output for, and then test it on a little bit of additional data that you still know the output for, but you haven't used that data to train your algorithm, right? So you have a training data set that you go to use, you go and use to set the weights through going through cost function, you go and minimize the error that there is on your training data set. And then you keep a little bit of data to yourself. This is again labeled data. This is data that you know the output for, but your algorithm hasn't seen it before. So this is your test data. And then you again expose your algorithm to this new test data and you calculate the cost function again. The practical thing is that you want the cost function on new data to be as small as possible. The training data is great. You go and figure out the weights. But it's the new data that matters. It's where your algorithm will be working and then basically acting later on. So training data is important. Training error is important. You want to minimize those weights, but at some point you have to see what is happening to the error with new data. So training, as we mentioned, is setting those weights. Because labeled data is often expensive, what you do is that you go and take whatever data that you already have and divide it into two segments. You train your algorithm with a portion of that data and test your algorithm with the remaining data that your algorithm hasn't seen. We have a training data set and a validation data set. The validation is basically validating whether your algorithm is performing optimally or not. And then we said that often, if you have an algorithm with enough degrees of freedom or a function with enough degrees of freedom, as you increase the data set, as the size of the data set, as you have more and more samples in your data set, your training error, as you try to go and set those weights with the data that you have in that data set, slowly goes up, right? Because as you have more and more data points and you're trying to fit the function to them, you will have basically in some cases situations where you're not going to fit to all those data points. So think about trying to fit a line to a number of points in a space or on a plane. If you only have one point, well, you're going to have a very easy time fitting a line through it, and the error will be 0. If you have 2 points, you still can fit a line perfectly to those 2 points, and the error will be very small. But if you have 3 points, and then there is a good chance now that they're not going to lie on a straight line, when you feed a line to it, you will get some error. If you have 4 points, 5 points, 6 points, and so on and so forth, you will probably start to increase that error a little bit. So the training error will normally go up as you use a larger and larger data set. But as we said before, training error really is not our focus. We want to figure out the best weights. At some point, the weights are good enough. You want to see how this algorithm behaves on new data. And the good news is that with a larger data set, your test error often goes up as you increase the sample size, the number of samples that you're using to train your data. And the idea here is that, as you have more and more data points, and let's say going back to the idea of fitting a line to a bunch of data points, if you have more and more data points, hopefully you have a line that fits better to that data. And if a new data point comes up, you have now a line that is better describing the data. So your error will go down as you increase the data size, the sample size. And then we said, okay, so usually, if you go and think about the statistical learning or machine learning, everybody likes to have more data, right? So more data, based on what we just saw, means better performance on new data. And then so once you accept that notion, the other point is, how do we deal with the function itself? Where do we say that the function that we chose is a good function to describe the data and the relationship between the input and output or not? So think about, again, because the regression already from your statistics course, think about having, a few points in the space. If you have a first order polynomial, second order polynomial, and so on and so forth, you can actually, for a given number of points in space, you can come up with a function that matches all of those perfectly. But we said at the end of the story, how you're doing on the training data isn't really that important. The important part is that how your algorithm works with new data. If you fit to every point in your training data, that's great. From one point of view, you have minimized your error, training error, but the test error could be very large. So typically, this is what happens. So when you have model complexity here, for example, if you want to go back to the regression examples, model complexity is the order of the polynomial that you're using to fit to that data. So, order 1, 2, 3, 4, 5. So that's on your x-axis. And typically, your training error goes down with model complexity. So as you choose a more flexible model, you can fit to that data points better and better in your training data set. And that will just get improving, and there could be a plateau at some point because, your model may not be able to fit to all of that data, or there could be some inherent noise in there that prevents the error from going down to 0. But in general, if you have a very flexible function and you have enough data points to train it, your error goes down on your training data set. And usually with the test data, it's initially following the same trend. Well, obviously the error is a bit larger because it's a data that your algorithm hasn't seen before, hasn't been optimized for it before, and therefore you have a slightly larger error at the beginning, even for throughout the entire range for this model complexity variable. But that error goes down, right? Because if your data is a true sample from what is happening in the real world, once your function tries to fit to that data, your function will work better for the data that it hasn't seen as well. So your error will go down. However, at some point, your model may be fitting only to your training data or very, very well to your training data, and then it starts to perform poorly on new data. So what happens is that your test error shoots up as you use higher and higher, more and more complex functions. And ideally, you would like to be somewhere close to that bottom of this curve, right? So you want to do as well as you can. Remember, we want the function to perform well on new data, on things that it hasn't seen. So we would like to choose somewhere around here. The model, if we choose a model that is less complex, we do not have enough degrees of freedom in our system, so our model doesn't work on training data that well, and it doesn't work on new data very well. And if we go and choose a model that is too complex, the model fits to the training data really well, but it performs poorly on new data. And nowadays, with the immense amount of computation power that we have, this is usually the problem, right? So quite often, you are not dealing with a model that is not complex enough. That's an easy problem to solve. You add degrees of freedom to your function. You add layers to your neural network. You add higher order terms to your polynomial that you're trying to fit. That's an easy problem to solve. The problem that is not so easy to detect and solve is if you are overfitting to your training data, because you go and come up with this function, you have a limited set of data, you go and fit it to that, and then the error goes down and you're super happy. You go and show this algorithm new data, and all of a sudden, boom, something goes seriously wrong. And these are two different types of problems in the machine learning lingo and this field. If the model complexity is low, if you have chosen a function that does not fit to your data well because it doesn't have enough degrees of freedom. So let's say you have a spread of points in space and you want to fit a line to it, but the points that they come from a quadratic function. Your model is too rigid. It doesn't fit to that data very well. And we say this is a bias problem. Usually bias problems are relatively easy to detect and fix because with a high bias, with a function that is too rigid, you will have a large error even on your training data. If you, on the other hand, have chosen a model that has more degrees of freedom that is optimal, then we have a high variance problem. In a high variance situation, your error on training data is really small, but the error on new data or validation data can be large. And this one is relatively difficult to detect, right? So even if you go and do cross-validation, let's say you train on one portion of the data and test on the other portion, and then go and come back and say, well, you know what, I'm going to mix my data and take another set of data for validation and another set for training, and then I'm going to see how my function behaves under these kinds of circumstances, or retrain the algorithm and see what the differences are. At the end of the story, you may be fitting to that data set itself. And again, new data can come up and mess up your function altogether. High variance is the problem that we often try to figure out, and then it's the one that basically keeps everybody busy. Now, so we just covered this. What can we do to address high variance or having a model that is too flexible? Usually, if you collect more data, you make it harder for your function to fit to all of those new additional data points. So collecting more data is usually the first solution that people will put forward, but it's expensive. Right? So if the data is coming from a source and you've captured it and you've stored it and now you want to go back and redo the experiment or collect more data, it could be expensive. Now, the other option is that, okay, so you have this function, it is overfitting to their data. Let's go and get rid of some of the degrees of freedom that you have. And this could be a bit tricky, right? So how do you know which features to drop? From that model that you have, let's say a vector that is n plus 1 by 1 and weights that is n plus 1 by 1, you want to go to some, let's say, k that is smaller than n. How do you know which features to drop? What makes you confident that if I drop this feature, I'm not dropping an important feature? And in engineering, sometimes you have an intuition. You should have an intuition in most cases to see, what features are more important than the other. But there are formal ways of analyzing these as well. There are methods like principal component analysis that they go and see if you have a set of inputs to your function and your function is responding to those inputs, which one of these caused the largest change at the output, right? So you basically x1, x2 to xn, which one of them is the most important, is the most influential when you look at the changes at the output. And you rank them based on their influence and then maybe get rid of the bottom 10% of those features. Again, in engineering applications, that may not happen as often because it works great if you have 100 features, 200 features, 300 features, and you want to simplify your life by getting rid of some of those features. But if you only have 3 or 4, which is possibly the case in engineering situations, or maybe 5, each one of them can carry a lot of information. So in most cases, you have to go back and rely on the physics of the problem and your intuition. And, it doesn't hurt to get some help from principal component analysis or other techniques. But at the end of the story, in engineering applications, you want to remain attached to the physical world. Do not rely entirely on a computer to do the job for you. And then the last option, or a very common option that people use anyway, is regularization. And regularization is the technique that we use where, if you have a set of weights for a set of features, we impose conditions that make it very hard for a few of the features to dominate. So basically, we gave a penalty for having super dominant features. We try to take into account all of the features, and this technique has shown to improve both bias and variance issues, but specifically in most cases we use it for reducing variance. Then again, it works great if you have tens or hundreds of features, not so great if you only have 3. And if you have only 3 features or 4 features and you want to choose between them, regularization, actually there is an additional benefit to it, that it actually avoids singularity in a lot of cases. So you basically get all the matrices that can be inverted and all that. So it's a good idea from that point of view. But in engineering applications, again, if you have 5 features, you should be on top of the problem, right? Don't let the computer decide for you. So that's that, from this moment forward, I'm going to go and focus on the new material, which is going to start with regression. Why do we start with regression? Well, a couple of reasons. First of all, you've seen it before. It is in your statistics course or other engineering courses, engineering math courses, you have seen regression. You know what the problem is and what we want to do. But now we are going to look at it as a machine learning algorithm. And then what we learned through this process of, let's say, having a new look at this problem and then what we've seen before, hopefully it eases you into that entire field. So what we want to do in a 2D case, as shown here on a plane, is to find the equation for that line. You can see it in there. that best describes the relationship between the input and output. So in this case, you will notice that the data we have collected has a good amount of noise in it. What is the best data that has the best line that will describe this data set, this input-output relationship with the least amount of error? So in a 2D case, when you have only, let's say, one feature, you will have a line. The first term there, W naught, X naught, remember X naught is 1, accounts for the biases, where this line is from the origin at X equals 0. And then W1 gives you the slope. So this is if you have one measured or calculated feature. Remember, X naught is always 1. But in most cases, you have more than that. So instead of having a line on a 2D plane, you may have a plane in a 3D space, or hyperplanes in higher dimensional spaces. But the algorithm at the end of the story is the same. What does linear regression do? It goes and looks at these X0, X1, X2, and all of these, and tries to come up with values for W0 to Wn, where the equation of that hyperplane or plane or line at the end of the story best describes the relationship between those input features and the output. So that's what we want to do. So we put the first term outside of that sum, but it's W0 X0. So you can actually put it in there and start the counter from 0. But we can also put it outside. So the X1 to Xn are measured or calculated features, and X0 is the bias offset, whatever that you want to call it, that we add to the function. Well, remembering that X and W are vectors, I can write that sum as a vector product. I'm going to show you how we can actually calculate the weights in a very, very simple way that is easy to follow. So that's the reason for writing these pieces of equation here. Now, we call it linear regression because your function is a linear function of W's. We don't care about X's here. It's a linear function of W's. If you look at that, I only have the first order of W0 to Wn. As long as you have that condition, it is linear regression. You can have a polynomial of order, I don't know, n here. So it could be W0 X0 plus W1X plus W2X2 plus W3X3, meaning that all those other elements in your feature vector are higher order values or higher order terms of the first feature. That's fine. You're fitting a polynomial to your y or as a function. But the weights are still basically W0, W1, W2, independent and first order. Now, the cost function we define here, and again, you've seen it before, is the sum of the squares of the differences between the predicted values and true values. So for each input vector x, I get a corresponding value y from my input data. I also calculate a value y. And then the cost function says, okay, what is the difference between what I calculated and what the true value was? This could be positive or negative. In order to get rid of that sign and focus only on the difference itself, we square it, and then we do this for all of the samples that we have. So we sum up the errors over all of the samples. The idea is that I go and find W0 to Wn such that this error is at its smallest. And this is basically it, right? So the calculated part minus the true value for each sample, sum over the entire data set. We want to find W's. By minimizing J, we want to find those W's. So what do I do? If I want to minimize a function as a function of a certain variable in that function, I take the derivative with respect to that variable, set it to 0, and figure out what the parameters for that function are. So this is what I do. Take the derivative of the cost function with respect to W. W0, W1, W2, W3, W4, and so on and so forth, and set it to 0. And this is what I get. So the derivative of this expression with respect to W0, when I calculated it, only this time is a function of W0, so it just comes out of the power series, and at the end of the story, this is what you get. When I do it for W1, similar thing happens. So instead of X0, I get X1. For Wn all the way to Wn, I get a similar expression, right? So I get X0, X1, all the way to Xn, and I need to set them to 0 to figure out what the best values are. So this is the formal approach. Let me go and see what happens if I write this in vector format, right? So I want to minimize that weight vector, the cost function. So I take the derivative with respect to each one of those weights. I saw from the previous page that at the end of the story, that's the equations that I get, right? So X0 times that expression, it should be 0, X1 should be times the same expression should be 0, X2, X3. I can show it in vector format, as you can see here. So I have one vector here, xw minus y, basically the predicted value minus the true value, and that is multiplied by x's. So what I can do is that I can take this x dy, put it on the other side of the equation. The goal is to find w, so what I can notice is that if I multiply this side of the equation by x dx inversed, I should be done. So that's what I need to do. I have my input feature vector, transpose it, multiplied by x, invert it, multiplied by x, and multiplied by y, and I get my weights in one shot, right? So if you want to calculate the weights for your regression algorithm, that's it, one line formula, and that you can easily implement in software, desktop computers. That's super easy. Microcontroller is not a big deal either. Now, couple of terminology if you haven't seen them before. If you notice, we multiplied the left side of the equation by x dx inversed, right, so that you get the unity matrix here. The term x dx inverse times xt is called the pseudo-inverse of matrix X. Why? Because if you multiply this by X, you get the unity matrix, right? As you show, if you multiply this matrix by X, you get the unity matrix. So it's called the pseudo-inverse because X may not be a square matrix. Usually we only had an inverse of a square matrix. In this case, X most likely is not a square matrix. But nonetheless, if you multiply it by this combination, we get the unity matrix whose dimensions are n plus 1 by n plus 1. It's a very commonly used feature. The pseudo-inverse is used a lot in linear algebra. And there are cases that you may not be able to invert that x dx. Right? And then if you cannot invert x dx, t means transpose, then you're in trouble because you cannot basically calculate the weights according to that expression that we shown here. When does that happen? When you have features that are redundant. Right? So for example, for the house price example, if you go back, let's say you have the area of the house in square meters and you have the area of the house in square feet as well. They are the same thing. It's just a coefficient that is changing one from the other. So they are not independent from each other, these two features. They're dependent features. So in cases like that, you can get a matrix that cannot be inverted. Another case is where you have features or you have fewer features than the degrees of freedom in your function. So let's say you're trying to fit a third order polynomial that has 4 constants, right? So coefficients, let's say the bias, the x0, w0, then w1x plus w2x2 plus w3x3. So you have 4 variables here, but your data set only has 3 data points. So, regardless of how you set this up, you have more equations than variables. And for that reason, sorry, you have more variables than equations. And because you have more variables than equations, you cannot find a set of values for all of your variables, in this case, your weights. So if you have too many features, you may not be able to invert that function as well. And this is where it shows, right? So basically, if m is less than n, that shouldn't really happen. If that happens, it just tells whoever that is on the other side of the table that you do not know what you're doing. Right? So okay. If you are using MATLAB for your machine learning calculations, which is what we are doing for the labs in this course, you can use the function pinv. This is going to give you the pseudo-inverse. And just at the end of the story, in terms of complexity, how complex it is, or how difficult is it to calculate the weights for a linear regression algorithm? Well, at the end of the story, the most difficult task here is to calculate and invert an n plus 1 by n plus 1 matrix, right? And that really isn't a big deal nowadays. If you're using a desktop computer, an n of 10,000 is not a huge deal. 10,000 by 10,000, that's 100 million elements. A lot of computers can nowadays do that inversion in memory. However, in engineering applications, well, you have a microcontroller and maybe you have hardly a megabyte of memory or so. So you're much more limited in terms of resources. But in engineering applications, you really don't have 10,000 features, or you shouldn't normally have 10,000 features. You're dealing with 10 features at most, or maybe more likely 5 features or so. And that means that you're inverting an 11 by 11 matrix. And that can easily be done with the limited amount of RAM that you may have on a microcontroller. So you don't really have to go and use other, let's say, techniques for inverting that matrix and then finding the minimum for the cost function. But if you need to, there are techniques that people have developed over the years. One is called gradient descent that is used very often in this field. And basically for very large data sets and then complex functions, you can do that. But as I said, in engineering applications, we normally don't have to. Now, let's have a look at one example. Let's say you have a sensor that should follow this pattern, should produce data along this line, but because of noise and let's say the user error and all that, when we do the measurements, we get a data set like that. So instead of having everything perfectly on that line, we get something that is above and below the line. Now, we go and feed the data line to it, basically, and through regression, you get the orange line or dark orange line here. It's not perfectly matching the original, let's say, source of that data, but it's pretty close. You can see that. And the more data you have, hopefully, if you collect your data properly, the closer it will become to the real line. Now, as we said before, it's called linear regression because your function is a linear function of weights, but it doesn't say anything about what your features can be. And then you can have non-linear features. So basically, you can have a second feature, or the second feature in your feature vector could be the squared value of feature 1. And the third one could be the cubed value of feature 1. And the fourth one could be the product of, I don't know, feature 2 and feature 4. All of those combinations are possible. So for example, you can have a function as shown here, where you have 2 features, let's say, that you measure, but you also calculate a third feature that is the product of those 2. And you have a fourth feature that is the first one squared, and you have the fifth feature that is the second one, the square root of the second one. And that is still a linear regression problem, right? Because this whole function, when you look at it, you have 6 independent weights, and all the weights are basically of order 1. How do we know if a fit is a good fit or not? Well, one way of quickly determining that is to use the coefficient of determination, R squared. You have seen this, I'm sure, in a lot of graphs, that people go and report an R squared value of such and such as an indication of how good their fit is to that data. What it is basically you go and look at the spread between, or the difference between the estimated values and true values. So for each value that you have in your data set, you go and say, well, the true value was here, the estimated value was here, so this is the difference. And then for the next point, maybe it is the opposite. Maybe the estimated value is a bit higher. And there is going to be a little bit of difference from point to point, right? So you go and calculate this over the entire data set, and then you normalize it by the variance. The variance is the natural variation in your data. So when you look at the denominator here, this is essentially your variance, right? So divided by 2m and by m, and you get your variance. And this is the spread, the differences between individual predictions. So you go and look at that spread, normalize it by variance, and then you try to make a judgment. If compared to variance, that deviation, that difference is small, we have done a good job. If compared to variance, that deviation is large, we may have to go and figure out a way to improve our performance. So here's an example. With that data, if I fit the shown line to it, I get an R squared value of 0.91, but with a slightly trickier data, in this case, it doesn't look like a line or a linear function would be a good fit or a good choice here. I get a smaller R squared value, right? So it's an R squared value of 0.7. Typically, when we have a good fit, your R squared value is one of the numbers that we can check, and it should be, somewhere around 0.9 or larger. Usually, 0.95, in some cases 0.98, 0.99 is what people expect to see. Now, well, again, sticking with linear regression and revisiting some of the concepts that we had, let's see what happens when we choose a different amount of training data in terms of the fit that we get to the data. So assume that this is the original line, the original function, the blue line here, and we have sampled that function. This is what we got. Let's assume that we train with 2 data points. So originally we go and pick 2 of these data points, right? And train our algorithm, basically in this case feeding a line to 2 data points. And it's easy. You can do it. You get the line going through these 2 data points. Your training error is 0, right? Because you're perfectly matching to those 2 data points. However, as you can easily see here, you're doing a poor job in terms of fitting to the rest of the data points. So what happens is that this is what you get. Your training error is 0, but you have a relatively large test error. I hope this is clear at your end when you're looking at this later on. But this is my training error here, test error up here. So if I go and increase the number of samples to, let's say, 3, all of a sudden, just by increasing the numbers, adding 1 additional sample to it, you can see that all of a sudden I get a line that actually looks much better, closer to the original line. My training error, unfortunately, shoots up, right? Because all of a sudden, my line doesn't fit or doesn't go through any of my training data points. But look at what happened to the test error. It's also a little bit high. Do this a few times. Now with, let's say, 7 or 8 data points, you get a line that actually is resembling your function. It looks like pretty well. It looks like it's much, much better than what we did before. Your training error has gone up, but it's not shooting up too much. The test error, the one that is important, is keeping dropping, right? So we're doing a good job by adding the number of data points for our function to feed. And if I keep going like that, and then ultimately, let's say, use 20 data points to feed to the data. Now you can see this function, the orange one, the line that I'm predicting the regression line is very close to the main line. My training error keeps going up. We saw that, as you increase the model, the sample size, your training error goes up because you calculate the error over a larger and larger data set. But my test error, which is the error that I really, really care about, has dropped. And as actually you can see here, it has kind of plateaued. It doesn't seem that I'm gaining much after the 20th sample. It looks like that the first 20 samples gave me a good enough function. Beyond that, it doesn't really make that much of a difference. It doesn't really hurt. If you have the data, use it. But it looks like that we basically are doing as well as we can. With this data and based on the amount of noise that there is in this data, this is probably as best as we can do. Of course, you can go and set a bunch of new numbers from your data and train it on a new set of data points and see what happens. But chances are that because there is so much noise in this data, your performance will not be much better. But do it anyways. Computation is cheap. Now, effect of model complexity. Now let's look at this case where we have a set of data points and we want to see if we can figure out the function that produced that data. So initially this data came from a quadratic function. This is the function that produced the data. We collected some data that is produced by this function plus some noise. So it doesn't exactly fit that curve. But in this case, we know what the function was. In reality, in most cases, we may not, right? So you go and try different functions. If you choose a line, you take, let's say, a bunch of those data points and you choose a line. This is what you get, a linear function. This is how it fits to this data. You have a fairly large training error and a fairly large test error as well. Go and increase the order, a second order function now. It looks like it's fitting the data much better. Both of those errors drop down. The training error is low. The test error is also low. But you can keep going, right? So you can go and try to use a third order polynomial, which is actually more than the original function, right? But you don't know. In most cases, you don't know. And it looks like that, your training and test errors are still relatively small. But as you keep increasing the order, you will see that your training error keeps going low, going down, but your test error starts to creep up, right? So what that means is that you're perfectly fitting to the data that you're using, or very well fitting to the data that you're using for the training, but you're starting to have a hard time fitting the new data. And as you keep increasing the order, this is what happens. So this is the curve that we saw before. With model complexity, the training error keeps going down. You can see that you're doing better and better with each iteration, perfect. But the test error, the one that matters, goes down, but it starts to creep up eventually, right? And it becomes really bad when you use a 10th order polynomial, and that's the fit. You can see that it's trying to fit to the training data well, but new data will give you a hard time. So where do I stop? If I don't know the function that produced the data, probably somewhere around here. This is where I had the least amount of error. Somewhere between 2 to 5 maybe is good. I had a quadratic function, so if I choose an odd order here, let's say third or fifth, I may be in trouble because those things inflict up. But I don't know, right? So for this reason, it's always good to have data as much as you can, but I'm sometimes limited to what I can see. How do I choose that polynomial order? Again, in engineering applications, go and use your engineering intuition. If you're looking at, let's say, a nonlinear phenomenon, let's say electrostatic actuation, you saw that it was proportional to voltage squared. So, and if you're fitting to that, keep V squared, V, and maybe a bias. You probably don't need a bias, but maybe a bias. So you only need 3 terms. Don't go above that, right? So use your engineering intuition in cases where you can. And I would just always use it as a base and maybe go slightly above and below and see what happens. But keep your engineering intuition in the play all the time. So that's that for linear regression. And this is basically the only algorithm we're going to talk about. This is the main algorithm that everybody is using anyway. But now I'm going to use this base that we've made so far to transition into classification. And then the first classification algorithm that I'm going to talk about is logistic regression. Doesn't really have much to do with linear regression as we talked about. But you will see that some of the functions and formulas are similar. And that's why we're going to talk about it next. So that's that for linear regression. We're going to start the classification algorithms from the next lecture video.